Alright, so today we're going to be dealing with Karnaugh Maps. Karnaugh Map is a very important and very useful tool in digital electronics. It allows us to actually find the minimum sum of product expression for related to any unsimplified expression. Any digital circuit, we could actually come up with the truth table and utilize that to utilize Karnaugh Maps to come up with the minimum sum of product expression. Right, so what I'm going to do first is introduce you all to what a Karnaugh Map is, and I'm going to use a 4-variable Karnaugh Map, and then I'm going to give you all the rules to using Karnaugh Maps to find the minimum sum of product expression. Right, and then we're going to do a number of examples. So let's begin. So what you're actually seeing here is a Karnaugh Map. There are 4 variables in this related to this Karnaugh Map: K, L, M, and N. Now, this is a 4-variable Karnaugh Map, so what happens is when we draw the Karnaugh Map, it's normally 2 variables on one side and 2 variables on the other side for a 4-variable Karnaugh Map. And what happens if we were to have, say, a truth table, right? We would actually make the Karnaugh Map will actually be like a matrix of 16 squares, right? So for instance, if from the truth table we actually have K, L, M, N, and the values for each of them are 0, 0, 0, 0, we're going to actually look at the corresponding value of the output, right? And when we look at the combination 0, 0, 0, 0, whatever the output is, we're going to actually install it in that box, right? So in another video, I'll show you all how to fill out a Karnaugh Map. But for this video, we're going to just be dealing with looking at a completed Karnaugh Map, right? And actually finding the minimum sum of product expression for that Karnaugh Map. So there are some rules that we have to follow when utilizing Karnaugh Maps to find the minimum sum of product expression, right? So normally, and let me just refer back to this, and we can see both of the Karnaugh Map and the writing there. So the rules. Now, every square that we have in here, this Karnaugh Map, is going to be represented by an expression, right? Our goal is to actually circle the ones, right? So the Karnaugh Map you're seeing here was actually utilized to find the minimum product of some expression, right? So just bear with what you're seeing over here. Normally what we do is if we want to find the sum of product expression, we have to circle the ones. And our goal is 2 things. We have to find the greatest or largest circles of ones in powers of 2 to the n, where n is 0, 1, 2, 3. So that means we can only circle 2 to the 0, which is 1, 1, 2 to the 2, which is 2 to the 1, which is 2 ones, 2 to the 2, which is 4 ones, 2 to the 3, which is 8 ones, and so on, and of powers to 2 to the n. Our goal is to circle the largest groups of ones that we can find in the Karnaugh Map in powers of 2 to the n. So that's the first rule. The second rule is we have to find the least amount of large circles based on this rule, the least amount of large circles that covers all the ones. So all the ones have to be covered, but we have to find the least amount of large circles that could do that. And another thing is it does not matter, we can recircle ones that have already been included in a circle, right? So what you're going to realize is, as we actually find the greatest or largest circles of ones, the greatest or largest circles of ones guarantee that we have the smallest expression, right? So for instance, if I have a circle, and I'm going to show you a circle with 4 ones, right? Or let's start off with a circle of 1 1, right? From a 4 variable Karnaugh map is going to have a 4 variable expression. If we circle 2 ones, it's going to give us a 3 variable expression. If we circle 4 ones, it's going to give us a 2 variable expression. If we circle 8 ones, we're going to have a 1 variable expression. So the more ones we include in a circle of powers of 2 to the n is going to give us a smaller expression. And so that is tied to number 1, right? The least amount of large circles we have minimizes the amount of expressions we will have. So together, these 2 rules will guarantee that we have the smallest expression. And that expression, once we follow all the rules, is going to be the minimum sum of product expression. Okay, so let's work out a beginner question. It's going to be a 3 variable Karnaugh map, a Karnaugh map that has just 3 variables. I've already prepared the Karnaugh map. All that is left for us to do is to apply those rules to find the minimum sum of product expression. So I'm going to go in detail with the first example, and as I go from example to example, we're going to actually speed up things a bit. So let's begin. So in this example, we require to find the minimum SOP for the function a f a b c, and this is the Karnaugh map. So what we're going to do, our goal is to find, remember the 2 rules, the largest circles of ones of powers of 2 to the n, which means n, if n is 0, 1, 2, 3, 4, the circles should be restricted to 1 1, 2 ones, 4 ones, 8 ones, and so on. And we have to find the least amount of big circles. So we look at this over here, and one thing you have to realize is we can include 4 ones in a circle over here. Now, one thing to note is that the ones could actually wrap around. The circles could actually wrap around on the edges. So we have 1 square or circle, right? And I may use square and circle interchangeably. Alright, just know it's the same thing, square of ones or circles of ones, right? So we have a circle or square of ones, 4 ones, right? From this Karnaugh map. So which means we're going to have 1 expression, right? Now, how do we find that expression? Let me give you all the long approach, right? The long approach requires us to look at each one and find the expression corresponding to that one, right? Now that one is what we normally call an implicant. So for each implicant, we have to find the expression. So let's begin with this one here. If we look at it, A is equal to 0, B is equal to 0, C is equal to 0. So whenever we have an expression for, let's say for instance, we have x equals 1, we actually denote that by x. And if we have x equals 0, we actually refer to that as x complement or x bar, right? Or x prime, right? So we get the expression for this by realizing that A, and you all didn't see that one, if x is equal to 1, we refer to that as x. If x is equal to 0, we refer to that as x prime or x bar. So same way, we look at this one here, we realize for that one, A is equal to 0, B is equal to 0, and C is equal to 0. So therefore, we actually get the expressions A prime, B prime, and C prime. So therefore, that one is represented by the expression A prime, B prime, C prime. What about this one here? A is equal to 0. A is equal to 1, sorry. So there's a little correction in this Karnaugh map. A is equal to 1, B is equal to 0, and C is equal to 0. So therefore, that expression is going to, for this one, is going to be A, B prime, C prime. What about this one here? That expression, A is equal to 0, B is equal to 1, and C is equal to 0. So therefore, that expression is going to be A prime, B, and C prime. And what about the last one here? This expression, A is equal to 1, B is equal to 1, and C is equal to 0. So that expression is A, right? It's coming off a little bit. A, B, and C prime, right? So this expression corresponds to this one here. This expression corresponds to this one. This expression corresponds to this one, and this expression corresponds to this one. So based on this now, tell me what is the common expression for all four of these? It cannot be the A, because we are seeing that for the four expressions, for the four ones, A is not common. A or A prime is not common, so we cross out that. What about B? B is not common also. B and B prime, some of them have B prime, some of them have B, so we cross that out. What we realize is common to all of those ones is the expression C prime. So as a result, this entire square or circle that with ones is represented by what is the expression that is common to all of them, which is C complement. So therefore, the function F, A, B, C, D, or not D, D is not there, it's a true variable. F, A, B, C is equal to C complement. That's the sum of product expression. So the sum of product expression, let me write it over in red. F, A, B, C is equal to C prime. So that was easy, and since it was that easy, let's do another one. So we have another Karnaugh map. We're required to find the minimum sum of product expression. In this case, the output is G, A, B, C. So we're going to find the expression, sum of product expression for that output G, A, B, C. So first thing we do, we have to find the biggest circles or squares of ones of 2 to the power of n. We are seeing 4 ones here. Right? 4 ones. So we could immediately go and find the expression. Now let's use the shortcut expression, the shortcut method. Right? The long cut method requires us to actually find all the expressions for the individual ones. Right? And I could actually try it. Let's try the both methods. Long cut method. This one, the expression is A prime, B prime, C prime. The expression for this one is A prime, B prime, C. The expression for this one is A prime B C. The expression for this one is A prime B and C prime. So what is common to all of them? A prime. So therefore the expression for this one is A prime. If I was to use the shortcut method now, it means that I'm going to look at this expression from this direction and see what is common. I see A equals 1 is common, right? So the shortcut approach, A equals 0 is common. So therefore, the expression A complement is common to all of them. I'm going to look at it from this side, vertical now, and see if there's any expression for B and C that is common to all of these ones. I'm realizing that A and B and C, the expressions are different for all of them. So therefore, B and C do not matter. So therefore, the expression for that circle is A complement or A prime. Right? So that's the long method and that's the short. And the goal is to eventually practice enough to be able to use the short method. Right? Let's look at the next, if we could get any more ones. Yes, we can get more ones. We have two uncircled ones that we need to circle. Now, if we circle these two ones, we are going to get a 3-variable expression. That makes no sense. If we circle these ones with these two ones here, we're going to get a 2-variable expression. And it's okay for us to recircle ones that were already circled. So the other square or circle is this one. And the expression for it, and we're going to use the shortcut expression, the shortcut approach from here on, is going to be, we are going to look at the square, these 4 ones, from this perspective, and we are going to see what is common. Looking at this perspective, none of the ones have a common A equals 0 or A equal 1. A changes for 2 of them have A equal 1, 2 of them have A equals 0. So therefore, A does not matter. Now it comes down to looking at it from vertical perspective. What is common? We look at these ones from the B and C axis, and we realize that B changes, but C is the same for all of them. All of them have C equals 1. 2 of them have B equals 0, and 2 have B equals 1. So therefore, B changes. So therefore, C equals 1 is what is common to all of the ones in this square. And C equals 1 is equal to C. Expression is C. So the expression for this circle or square and this one are these expressions. So therefore, the sum of product expression for GABC is equal to A prime plus C. Right? And that's the expression. A prime plus C is the sum of product expression. Okay, so let's step up to 4-variable Karnaugh map, and I have already an example lined up. So let's go ahead with that. This is a 4-variable Karnaugh map. We're required to find the minimum sum of product expression. Of course, the output as usual is f of A, B, C, D. D being the 4th variable. So how we do this, first thing we do is, of course, we apply the same rules. Largest circles of ones, circles or squares of ones of power 2 to the n. And then the least amount of those large circles. And once we circle them, then we go about and find the expressions for each of the circles of ones. So if you look at it, first thing, we look here and we see a square or circle of ones, 4 ones. So we circle them, right? And immediately let's get the expression. The expression for that is, looking at the horizontal side, what is common? It's A prime. B is irrelevant because it changes it's different for all of the ones in this circle. Let's look at it from vertical now. What is common? Right? C prime. C equals 0 is common for all of the ones. So therefore, that expression on that side, we complete it with C complement. So that square or circle, this is the expression representing it. Let's find another circle. We are seeing 4 ones here. We've seen 2 uncircled ones, but we could actually use 2 circle ones along with them to get a smaller expression, right? So from a 3 variable expression to a 2 variable expression by just including those other ones here. So we're going to circle that. And it's easy for us to find the expression for that, because if we look at downwards, C and D values vary for each one here. But if you look at from a horizontal perspective, A equals 0 and B equals 1 is common to both of them. So therefore the expression for this one is A complement B. Now the last thing is we have an uncircled one here. It makes no sense of circling this one by itself because it's going to give us a 4 variable expression. But if we include the circle one in a circle with that one, it's going to give us a 3 variable expression. So let's go ahead and do that. And the expression for that is same procedure. We look vertical and we look horizontal. So let's look horizontal first. We see that A and B, A is equal to 0 for one of them, A equals to 1 for one of them. B equals 1 is common to both of them. So therefore, one of the parts of the expression here is B. Look vertical and we are seeing that both ones satisfy the C equals 1 and D equal 1 condition. So therefore, C equals 1, which is C, and D is equal to 1. So therefore, the expression for that circle of 2 is B, C, D. So therefore, our expression, minimum sum product expression, F, A, B, C, D, is equal to A prime, C prime, plus, right, A prime, C prime, which is this one here, plus A prime, B, plus B, C, D. And that's the minimum sum of product expression. Now, one thing to note that we call it product terms. They look like product terms, but when I did Boolean algebra with you all, you would understand why we actually call them product terms and why we call them sum terms, right? So we sum up, right? It's really or and expressions here, but you learned that previously. So that's why we call it sum of product expression. And that's how we did it for this one. Okay, so we're gonna do one more, and I'm gonna actually make sure this is a tricky one. So let's go ahead with that. So we're required to find the minimum sum of product expression. I left out a couple of zeros. Let's put that in. Minimum sum of product expression for this, for the output F, or let's use another output Q, A, B, C, D. So first thing, let's go and get the biggest or largest circles of ones and the least amount of them. So the first thing you have to realize, I am seeing 4 ones in one circle here. And that is because the corners actually wrapped around, they're actually in one square, right? So therefore, this, and this is one square or circle with 4 ones. So look out for that. Always look out for the corners being wrapped around, or look out for those corners here that could end up in the same circle, right? Look out for that. And also we get another, we have 2 ones here that we circle, so we circle those 2 ones here. Let's find the sum of product expression. First find the expressions for each. So the 4 ones in that circle, let's look at it horizontally. What is common to all 4 of those ones? What is common is nothing to do with A, nothing to do with A equals 0, A equals 1, but everything to do with B equals 0. So therefore the first part of our expression is B prime. Let's look downwards. Same thing. D prime is what's common to all the ones. So D prime, B prime, D prime is the expression for that square. What about this square or circle? Same thing. A prime, B, and what's common looking down? D. So the minimum sum of product expression is equal to B prime D prime plus A prime B D, and that's it. Alright, so we looked at a couple of Karnaugh map examples. We did some three variable Karnaugh maps, some questions with 4 variable Karnaugh maps, and you all learned the theory around the use of Karnaugh maps to minimize expressions to the simplest form, to the minimum sum of product expression form. So this concludes this session, so I will see you all on the next one.